All right, so we're going to look at the ideal gas law today. It comes from the gas laws that you studied already. If we look, we know that when pressure goes up, volume goes down. When pressure goes up, temperature goes up. And when volume goes up, temperature goes up. The only thing we're going to add into it is an amount, how much gas there is, which is N in our equation. Well, if we're adding more particles, pressure is going to increase because we're going to have more collisions. Volume is going to decrease because they're going to take up more space. And temperature is going to increase because there's more stuff in that. So, if we're going to look at the combined gas law that we've looked at before, P1 V1 over T1 equals some sort of constant K, we can look and see that N has basically the same relationship as T. So now we can rewrite this as P1 V1 N1 over T1 equals K. Now when we're looking at it in this form, we stop using constant K, and instead they replaced it with an R. R is the ideal gas law constant. It's got three values that you need to worry about. R is equal to 0.0821 when you're in atmospheres. It is 8.314 when you're in kilopascals. And you don't have to worry about the other one. Remember, this is just a quick recap of what's in your notes that you should be looking at already. So, with that being said, I'm going to erase the board now and solve out the practice problems that are in the slideshow that you should be reviewing before you watch this. So, if I erase this, we can look at the first practice problem. First practice problem asks what the volume of 2.16 moles of gas that's applying a 1.25 atmospheres of pressure on a cylinder in a room that's at 25 degrees Celsius. First thing we have to remember with any gas laws problem, we need to take our degrees Celsius and add 273 to it so that we're in Kelvin. So, we take 25, we add 273 to it, we get 298 for Kelvin. Now that we have 298 Kelvin, we can plug everything in. So we know that we're going to use PV equals nRT. That's the form that we usually use for the gas law equation. Instead of having it equal to a constant, we just rearrange it so that everything is not a fraction. So let's put in our variables. We have 1.25. We're trying to find the volume. It's equal to 2.16. That's the amount of gas that we have. 0.0821 because our pressure was given in atmospheres. And our temperature is 298 Kelvin. So we get 1.25 V equals 52.85. And if we divide both sides by 1.25, we get V equals 42.3 liters. That's problem number 1. Problem number 2. We have a 25-liter cylinder that has 1.5 moles of gas in it, and it's in a room at 115 degrees Celsius, and they want to know what the pressure was before the cylinder ruptured. So similar to what we did with the last one, I'm going to use PV equals nRT, and start plugging our numbers in. So we get P times 25 equals 1.5, that's the moles of gas. I'm going to use the ideal gas constant for atmospheres, but you could use a kilopascal one if you wanted to. 0.0821. And then our temperature, we had 273 degrees to 115 to get 388 Kelvin. So now we have 25P equals 47.78. Divide both sides by 25, and our pressure ends up being 1.91 atmospheres. All right. Next practice problem. How much gas is in a 7.5 liter cylinder at 5 atmospheres of pressure at a temperature of 15 degrees Celsius? So, still using PV equals nRT. We will plug our numbers in. This time we have 7.5 times a volume that was given to us. Oh no, that was my volume, sorry. Our pressure was 5. Multiplication, so it doesn't matter what order you put it in. We want to know how much gas. We're going to use 0.0821 because our pressure was given in atmospheres. And then 15 degrees Celsius is 288 Kelvin. So if we do out the math, we get 37.5 is equal to 23.64 N. So we divide both sides by 23.64 and we get N is equal to 1.59 moles. And those of you in A level, I'm going to let sig figs slide while we're on remote learning. I'll just pretend to hear your cheers right now. All right, last one that uses this version of the ideal gas law. We have a 10-liter container at 189.15 kilopascals, and it's filled with 3.5 moles of gas. It wants to know what the temperature is. So let's plug in our things. We have 185.91, did I say? No, 15. 189.15. That should be enough. And we're multiplying that by 10. It's going to be equal to 3.45 moles. That's how much gas is in there. And R this time is going to be 8.314 because we're using kilopascals instead of atmospheres. And we're trying to solve for T. So we get 1,891.5 is equal to 28.68 T, which means T is equal to 65.95 Kelvin. I have helpers at the door. They want to come in. You can't see them, but my dog Nava and her cousin Benji just came in to join our lesson. Because no chemistry lesson is complete without the doggos. Alright, a little later on in the slideshow, you saw two different forms of the ideal gas law. We saw one where you get M equals lowercase m RT over PV. This one is used to find the molar mass of an unknown. That's what capital M is molar mass. The other one you saw is D equals M, capital M, P over RT. This is used to find the density of a gas. We're going to be using an example of each of these now, and yes, they do show up on your test, so you do need to know how to use them. So, the practice problem I gave you for the molar mass read that there was 3.5 liters of an unknown gas, and it weighed 24.7 grams. It was at a pressure of 2.5 atmospheres at 25 degrees Celsius. We need to find the molar mass. So we're going to use big M equals little m RT over PV. So now, let's just plug in our numbers. Big M, our little m stands for mass, that was 24.7. R in this case is 0.0821. T, we were at 25 degrees Celsius, which is 298 Kelvin, over our pressure. Pressure was 2.5 atmospheres, times the volume of the gas, which was 3.4 liters. We plug all those numbers in, do the math out, and we get big M equals 71.1 grams per mole. All right, last but certainly not least, the density equation for ideal gas. And that again is D equals big M P over RT. Your practice problem for that, number 16, said carbon dioxide was stored at negative 17 degrees Celsius. It has a pressure of 7.3 atmospheres. What is its density? So, we plug in our numbers. The molar mass of carbon dioxide we find by looking at the periodic table, adding carbon and two oxygens together. Yep, stoichiometry hasn't gone away, folks. That's 44 grams per mole. Our pressure, we said, was 7.3 atmospheres. Because we're in atmospheres, we're going to use 0.0821 as our ideal gas constant. And our temperature was negative 17 degrees Celsius. Negative 17 degrees Celsius is 256 degrees in Kelvin. Do out our math, and we get our density equal to 15.3 grams per liter. And that's it, folks. I'll be online during your scheduled class time. Moderator will chat if you have any questions. We'll do a live check-in the last 20-ish minutes of class. But feel free during the live chat to ask questions, or during the Zoom meeting if you have things like that, because I can point my camera at a piece of paper and solve some problems up for you during Zoom. It just might be backwards. So, take care everybody, stay healthy, and we're in this for the long haul now.